I'm now going to talk about what we are going to discuss today. Now, if you recollect, what we went through in the last session was now we are starting the talk, and it's kind of an overlap with the previous one because I want you to understand this forward backward propagation very closely and important because that's the fundamental of AI deep learning. Because if you don't get this correct, lot of the problems will stay. And honestly, I'll tell you, if you don't get your forward propagation and backward propagation correctly understood, basically your journey in AI is sealed. You can't do much because if you have to build models and develop new models and all that, and nowadays we are expanding our models into so many different areas. We are starting a big project based on deep seek development. We have starting a material science cell. We already have, as some of you would know, a drug discovery story and a robotics story and a cybersecurity story. Now we are adding the material science story, which is again going to take about 30-40 people from our colleges. Plus, we are going to start another big LLM development. It's a different kind of LLM, agentic LLM development, which is again going to take about 40-50 people. If you have to get into all of that, and which I hope sincerely at least people who attend this session will do, I think you will need a lot of good background of AI and deep integration. So today we will walk through the forward integration, backward integration again, but this time I'm going to do it with Python code, which we got from that lecture of Jason Brownlee that is doing back propagation from scratch. I'm going to go through all pieces of code in that article, and we are going to explain, run that code, and make you understand each line of that code. It's important. It's important to understand each line of the code. Very, very important. I'm a little disappointed to see only about less than 250 people coming in. Well, I think that's the nature of the beast in this state. So that's okay. So what we are going to do today is we are going to develop a three-layer. Basically, it's not even three-layer. It's basically the input layer, if you were to call it an input layer, with a certain number of inputs, a hidden layer, this is a hidden layer, and an output layer. That's it. So this is a hidden layer, and this is the output layer, and with a certain number of neurons, which we are going to configure. So we are going to build this kind of a network. And obviously, if you have 3 nodes here and 4 guys here and 2 guys here, and we are going to do simple regression. So this is how this guy will develop. You know what this all means. These are the weight matrices or the weights, and so on and so forth, right? So this is also to be connected, and the same way this is going to get connected to this. This is also get connected to this. This is also getting connected to this. This is also getting connected to this, and this is how it all goes. And each layer is going to have an activation function, except of course the input layer. Input layer is just going to be taken into this hidden layer. And as I told you, normally in a real life network, this goes into thousands of layers. Okay. Today we have only one hidden layer, but there could be thousands of hidden layers besides the input and the output and the bias. So this is what is the structure. And I'm just going to remind you of the equation. The notional representation is, this is called X in our equations. So this weights is gives us Z. So Z in this case is W1. This is the weight matrix weight. W1 X plus B, that is Z. And then the output of this is going to be activation function. So let's call that output as A1 is going to be sigma times Z. That is basically the overlying equation. And again, A1, A1 becomes the input over here. So I'll call this Z1 and Z1. So these are the abiding equation here. for him, this I had explained at length last week. So I'm not rushing through it, but I'm kind of hoping that you have understood. So A1, which is the output here, is this. So now writing this in a similar equation is Z2 is equal to W2 A1 plus some B1 and B2. And then A2 is equal to sigmoid of Z2. And then A2 is same as Y hat. So A2 is Y hat. So that is what we look at it. Now output can also be 2 or 3, depends. So this is the output. So this is what gets created here or here. Okay, so this is the abiding equations. I think we had discussed these equations at length in the last class, and so I'm not going to again spend too much time on this. Yeah, we have started recording. Vikas, thank you for telling us. We missed the recording last class. We have started recording, so don't worry. Yeah, so that's the story which we have so far. This is our neural network. As I said, this can be a 1,000-layer neural network. So now we are going to develop the Python code for each of these layers. Now today we are not going to use any Python libraries. Any libraries. We are not going to use TensorFlow. We are not going to use PyTorch, none of those libraries. Neither are we going to use any Keras or anything. I'm slowly going to introduce those libraries to you. Today, it is plain vanilla Python code, which I'm hoping most of you will be able to understand and appreciate. The second years for sure should understand. The first years, I would be happy that they understand because I think they have started learning some Python on their own or whatever. In some of our colleges, we are doing Python in the first semester itself. And some of you, I am sure, are adventurous enough and pick up Python on your own also. And okay, so that's the story. So now, if then there is this loss and all that, and then there is a backward propagation, which we have kind of alluded to. Now, I'm not going to straight away jump into backward propagation. First, we are going to see how to implement a forward propagation itself. Listen very carefully. I'm going to go through pieces of code. And as I said, it is plain vanilla code. It is not using any libraries or anything as we normally would do. Our next versions of the programs will introduce TensorFlow, we will not do, not TensorFlow actually, we'll use PyTorch because we have not nowadays stopped using TensorFlow and Keras. We are all shifting towards PyTorch. And you will soon see the difference between the way we write it in PyTorch and the way it is written in pure Python. And you will then make out the difference and all that. But I would like you to get familiar with this also, so that you know you are clear. Okay. So the way I'm going to start is you know what the forward propagation should do. Basically, it should take and give you that y hat computation or A2 computation. So we will see how to implement each of those. Now I'm going to throw code at you, or rather I'm going to go through the handout or through the link, which is that Jason Brownlee link, and I'm going to go piece by piece, and we are going to walk you through the code and build that code, and then later you can try it out through the Jupyter notebook also yourself, how to write the code. Okay, so now let's look at that thing. So I hope I had alluded to this in the last session also. This Jason Brownlee. I hope I had shared this link also with you. Basically, Jason, if you want to search in Google, just say Jason Brownlee back propagation from scratch in Python or something like that, and you will get this. So this is the thing. This is about 4 years old, but it's good. It's a good thing which I always use to start our Python lecture. So it's a very good introduction to deep learning, and I found people who start with this do much better than the people who don't start with this, and therefore I'm starting with this. Now I'm going to show you the first block of code. You can read this article later. You can use ChatGPT also in conjunction with this article to understand what I'm talking about better. Okay, so let's start with the first piece of code from this, and I will show you what it does, and then we'll run it and see what it does and all of that. And I'll explain. Okay, now before that, well, this is the kind of data that we are going to start with. Actually, it is not important what the data is. I don't even know what that data is. It's basically there are 201 records, it seems, or there are some certain number of records. Each record consists of attributes and the label. Label is called the Y. Okay, so if you were to think about it, so here if you see, these are the 5 attributes. One, so this call it x1, x2, x3, I am sure there are 6 attributes, x4, x5, and x6. Did I miss one? No, there are 7 attributes, sorry. Not 6, there are 7, x7. Huh? And this is the label.
There are 201 records and 7 numerical input values.
Okay, so there are 201 records and 7 numerical input, and this is the label. So this is the Y, which you have to guess. This is your training data. So your training data consists of 7 plus 1, 7 aspects of X. You know, it's really not important what they stand for. They could mean blood pressure, they could mean weather data, depending on the kind of problem. And there's a label associated with that data. Okay, so this is how any data set will be given to you. There'll be the variables for regression. For imaging and all, we'll see later. You'll have images and the category of the image, whether it's a cat, dog, or anything, the class of the image. There will, our algorithms will also change, and the way we do things will also change. But here it's pretty trivial. There are 7 items of data and 1 conclusion. Okay, so this is what we will learn. We will train our network to predict. Now we will see whether we'll be able to predict or not correctly. So we will blind some data, we'll keep some data aside, and then check whether it is coming correctly or not. That we'll do later once we have developed the algorithm and trained it. So this is how it will look. So this is my data set. Okay, it is a very reasonably small data set, 201 records and 7 numerical variables. Okay, so let's move on and see how the forward propagation is built. Okay, this is some kind of seeds data set as they are telling us. Okay, so now, yeah, now we will first build the network, which is called initializing the network. This is the first step. We'll initialize the network, then we'll do the forward propagation, then we'll compute the back propagation error and learn how to back propagate it, and then we'll train the network, and then we'll see predict, and then we'll feed the seed data set and case study. This is a total example. Okay, so let's start with initializing the network. I don't mind going slow. It's important that you understand it. Okay. Now let's pause here and understand what this network means. Initializing the network means, and then we will try and do this. So this is the initialization of the network. Now, before I even go here, what does our network consist of, and what do these inputs mean? So let me, as I said, our network consists of 3 parts: our input, our hidden layer, and also the output. Okay, I'm just marking the output. Now, this is the number of outputs here. It can be single output or it can be multiple output. In the example of the data set, how many outputs would you need? Only 1, because it's either 0 or 1, I guess. So it's a binary output, so you'll need only 1. But I think the initial network they have built has 2 outputs. Depends on how it works. And there will be a certain number of neurons here in the hidden layer. So there will be a certain number of neurons. And then there will be X, that is each sample of X. In this case, X will be how long? It will be 7 items of data. Remember, there will be 7 items of data. And basically, depending on the number of neurons. So if there are 3 neurons here, and then there are 7 here. You know how many weights will be required. Each of these neuron here will need 7 weights to weigh in the input from all the 7. So these 7 weights will be required. So how many weights will be required in total? 21. If there are 3 neurons, there will be 21 weights required. The weight matrix will consist of, I mean, it is going to multiply this, so it will be 3 into 7 matrix. So basically, the 21 weights will be there, and the matrix will be a 7 by 3 or a 3 by 7, depending on how you look at it, kind of a matrix which will create, okay, for this. And then depending on the number of outputs here, so let's say that if there are 2 outputs, how for each one of them 3 weights will be required, so 6 weights will be required, right? If you have 3 neurons here and 2 neurons in the output, 2 outputs, though you may need only 1 output in this example, but depending on that. So, so these weights are getting created. So let's see how they are creating. So number of inputs, number of hiddens mean number of neurons here, and number of outputs, okay? So how does he build it? So he starts with network is equal to list. He can also say just this. Is building the network as a collection of layers. So the way he is doing is, the analogy is, each layer consists of neurons. Okay, each layer consists of neurons, and each set of layers become a network. So in this case, how many layers will there be? Depends on how you look at it. So we don't take input as a layer. So this is a hidden layer and output layer. So this is actually a 2-layer network. So how many series of weights? This is 1 weights and this is 1 weights. So there are two matrices of weights, or 2 lists of weights that we need to create. Now let's see how many weights and how are they organized. Let's look at the weights. Now let's look at the code, and then I'll elaborate what this code does. So now he is drawing the weights for the hidden layer. So this is the hidden layer. So this is the layer he is describing along with its weights. So how will the weights be organized? So how many sets of weights? 3 sets of weights, right? 1, 2, 3. That depends on how many neurons are there in this layer, and also the weights. How many are there? 7, and that is the number of inputs plus 1. That 1 is for the hidden for the bias, because we need to carry the bias also, then extra weight, which doesn't get multiplied by x, but it's there as a weight for every neuron. So look at it now. Now look at the data structure he's using. This is important. Hidden layer is equal to, now he starts each layer to make it a list. See this square bracket makes it a list. Now list has a so why is it a list? Because 1, 2, 3. There are three sets of weights here. Imagine that the hidden layer has 3 neurons. In this example, let's take a hidden layer as 3 neurons. So because the hidden layer has 3 neurons, so I'm just drawing. So there are these 3 series of so many. There are so each is a set. Each is represented as a dictionary in Python. So so how many dictionaries? 1 dictionary, 2 dictionary, 3 dictionary. This they have represented not as a each of the weight matrix is represented as a dictionary. Well, dictionary in the sense it is also a list, but it is tagged under weights. So look at this now. See this inner thing first. Just look at this first. So weights. So he's creating a dictionary with 1 field called weights. It's a dictionary with only 1 field, weights. And how is the weights created? How many weights do you need? You need 8 weights. Why do you need 8 weights for every neuron here? You need 7, which are going to feed into it. And they are all created randomly. Initially, the weights will be all random. So weights, random. For I in range, number of inputs plus 1. That is, number of inputs is 7. Plus 1 is the hidden, is the bias. So basically, the weights will be a list. There will be a dictionary of weights with 8 weights for each neuron. And how many such will have to be created? Now look at this part. Uh, can we scroll to the right? Yeah, we'll scroll a bit to the right. Now see, for I, just look at this now. For yeah, for I in range of n hidden. N hidden is this. This so many sets of weights have to be created. Remember, each neuron will need its own weights coming from the input, because that's how the network is organized. So that's how he has done. So it is if there are three, remember it is organized as three dictionaries, each with 7 weights, or rather 8 weights, 7 plus 1 weights. That is how this is organized. So actually, the number of weights here is not 21, it is 24 if you include the bias for each neuron, which is not dependent on the input, which is a fixed bias for each neuron, that is 1. So it is 24. So I need 24 weights here, and the weights are organized in lists of 8. That means in groups of 8. So the first group is 8, second group is 8, third group is 8. That group of 8 is represented as a dictionary with weights as the key field and 8 values listed against that item in the dictionary. So now I'll try and draw this, and then that hidden layer is created. Uh, uh, I'll draw this a little more in detail. So network dot append hidden layer. This is a hidden layer which contains all the weights. So layer means in this with the way he is developing, each layer has weights. Okay, see these very weights. So there are 24 weights here. Now output layer. So this is another layer. This is hidden layer. This is output layer. How many will there be? Again, if you take bias into consideration, there will be 7 into 3. If you take that, the 3 sorry 3. This will be 3 into 2. But each of them will consist of 4, right? 3 plus 1 bias. Okay, 4. So there will be 8. 8 weights here in groups of 4. Okay, again, how will that be organized? For I in range n hidden, so that is what it is. So again, you look at this, there is again a bias here. Output layer weight random for I in range n hidden plus 1. So these many weights in here for each weight in the output. So there many these many weights here for each weight in the output, because each one of them is connected to that. So you have to understand here that each of these neurons here, output neurons, will have correspondingly 3 weights, because there are 3 neurons. Again, each output will have 3 neurons here, right, coming to it. So it will be a dictionary of 3. 3 plus 1, 4. I always keep forgetting that bias. So there is 4. So there are 8 weights in this picture if we have 2 output neurons and 3 neurons are there here. So basically, this is what is the second layer. This is the output layer. And I add the output layer to the network. So this is what this initializing of the network. It has just built random weights for this layer and random weights for this layer. That is all it has built because of the random function. It just has picked up random weights and built that. So that is how the layers have been built for this AI. So how many layers? 2 layers. So 2 sets of weights. Now we are going to run this piece of code and just independently. That's the beauty of it, because it doesn't need any special library. We are going to open a Python library and copy this code and run it and just observe the output. In fact, that is what this piece of code does. Okay, so let's look at that piece of code and copy the code which is coming after that. So we'll just take this piece of code, no, the one below. It actually initializes the network. Yeah, okay. Let's run this network and I'll show you what it all means. Okay, we'll run this and then I'll show you what all it means. Uh, Okay, now let's do it a little before. Okay, no, let's pause. Okay, now let's see how smart you guys are. Now look at that initialize here. This is the same code which I just showed you, and now he is initializing the network with two inputs. Actually, this won't work for us for the present problem because we need seven inputs. He is having one neuron in the hidden layer, very small network, and two outputs. So now, can you guess how many for this configuration? How many weights will be required? Okay. Can you guess how many weights will be required exactly, totally? How many weights for the first layer? How many weights for the second layer? Add them up and tell us how many weights will be required here. Okay. So let's see how many of you get that right. Okay? Can you tell us how many weights? Yeah, some of you are getting it right. Uh, yeah, some of you are saying 7, some of you are saying 4. Okay, any more answers? No, I'm not doing a poll. It takes a bit of time. Yeah, 3 and 4 is 7. I'm asking total number of weights. Yes. Okay. So I think many of you got it right. Uh, okay. Let's count how many weights will you need. So let's try and draw the structure. So there are going to be two inputs. So your input layer has two inputs. Remember, there's also a bias, and then this is the hidden layer. It has only one neuron here. This is the one neuron, and it has two outputs. So two outputs. So if you were to draw this kind of a network, you would have for each one of them two weights because there's only one neuron, two weights plus the bias which is always there. So this layer will need about three weights, one bias for this neuron, and then there are two neurons here and one neuron here. So this will go there plus a bias. So that will require, for this also there is a bias, remember? So the bias, so that will be two weights there, and then there will be I mean, not weights will be not two actually, but there will be two inputs to it, by weight one and bias. So this way, and then this will also be connected again. For this also there is a weight and there is a bias. So there will be two. So totally 2 plus 2 4, 4 plus 3 7. Total number of weights in this network will be 7. Okay. Okay, so let's try to, and the seed one, you know why this seeding is done? So that we fix the seed, so that this random is based on the seed. It is derived from the seed. The random function will be not really random in the sense it will produce random values, but the same random values for you and me based on seed. So the values will be random, but they are determined by the seed. So if we both you and I use the same seed, then our random and your random will be one and the same. So that is why we use this seed. It triggers a seed for the randomization, and the output is obviously going to demonstrate the weights, and we will look at the structure. So let's run this code. Yeah, you got this right. Those of you who said there are 7 weights, you got that right. And let's run this network and see, what's the kind of output we are getting. We are running it in a regular, normal Python compiler, one of the online compilers, nothing very fancy. And okay, so you can see the number of weights which have been triggered. So you can see this is the first layer. Let's look at the structure. This actually illustrates the structure reasonably well. So let me use a red color. So if you see this weights, you see there, because there is only one neuron in the hidden layer, there are 3 weights associated with it. These are the 2 weights. Oh, I think I should change the color. I think yellow is better.
Yes.
Yeah. So there are, these 2 are weights, and this is the bias. So this is the bias. Okay, and these are the weights. See, they are represented as a list against the dictionary of weights. So that is how the data structure looks. Now this is the first layer, okay, or the hidden layer, and this is the output layer. Okay, there are the second layer. Now you see output layer, because there is two neurons there. Each neuron has one weight and one bias. Again, the second neuron again has one weight and one bias. So that's how this is coming through. So now, because there are two output neurons, there is two weights, two set of weights. Remember, there is two weights. There are two dictionaries, one for each neuron in the output. So there is this structure, and therefore there is this structure also. I think those of you who understand a bit of Python will immediately understand that there is a dictionary, but there are two dictionaries, because there are two outputs in the output layer, two neurons in the output layer, and each one of them has two weights. One of them is weight, one of them is bias, one of them weight, one of them bias. So that's how this data structure looks. I hope at this stage you have understood how he has built the network. So this is the whole thing is a network. Each network consists of layers. So this is the first layer and this is the second layer, and each layer itself is consists of, depending on the number of neurons in that layer, I mean in this case the hidden layer, in this case the output layer, that many dictionaries are there. So here there are two dictionaries. Here there is only one dictionary because there is only one neuron, and because there are two inputs, there are two weights for those two inputs and a bias for that input. So that is how this is created. Okay, so what we'll do is, just so that it settles well with all of you, we will create a slightly different network just to illustrate. We'll create a network with 7 inputs, and let's say with 3 hidden neurons, three neurons in the hidden layer and one output. So let's see how the thing works and how will I set it up. I'll just change these parameters. So this is 7. So there is 7 plus bias 8. We'll have 3 neurons in the hidden layer and 1 in the output. To mimic our problem, I mean, this moves closer to our problem. It can be something else also. So now, can you tell us, how many weights do you see and how are they distributed? So in the hidden layer, how many weights will we see? For each neuron, how many weights, and how many total number of weights in the hidden layer, and then how many weights in the outer layer. For each neuron in the output, how many, and therefore what is the total? Okay, so yeah, so I think most of you got it right. Totally there are 28 weights. The distribution is 24 and 4. Yeah, you're getting it right. Good. Some of you are making good progress, because if you are able to understand this itself is a good sign that you are developing the sense of weights. Okay, let's create the network and see how the weight matrix looks for a moment, and let's understand the weight matrix. Okay, so now we just ran this and you see the weight matrix. Let's examine it for a bit and see how it looks, yeah, and get a bit of insight into the weights. So I said, how many neurons are there in the hidden layer? 3 neurons are there. So for each neuron in the hidden layer, there will be 7 inputs plus the bias. So each neuron here will have a dictionary with weights, and how many weights will be how the list will be associated. The weights list will be associated. There will be 8 weights. How did we come to 8? 7 for the inputs and 1 for the bias. So that is how the weights dictionary will look for each of the neurons. And how many such things will be there? 3 of those. Okay, let's see whether that's working. So now we start with this list of weights. So each one of them, there are going to be 3 elements in this list. The first is the first dictionary, weights, and we are talking about the first neuron here, first neuron in the hidden layer, sorry. So there it will have 8 weights associated. 1, 2, 3, 4, 5, 6, 7, and 8. This is the bias. This is with the first neuron. Now you see the dictionary which is associated with the second neuron. Again 8, 1, 2, and it goes on. And this is the dictionary associated with the third neuron. That is the third neuron here, because we have 3, remember? The third neuron here, again 8 weights. So let's scroll down and check how the rest of it looks. This is the first layer. Okay, so that's it. This is the first layer. Now this is the second layer. So second layer is again one more list. So the first layer ends here, and the second layer begins. Second layer means the output layer. Now how many does it have? If you look here, 1. It has only 1 output, but 3 incoming plus bias. So it will have 4 weights. So it's a dictionary with there will be only one dictionary, and that dictionary will have a list of 4 weights. Okay, so this is a dictionary, only one element in the outer dictionary. As you can see, weights is occurring only once, and each has and that has 4 weight, 1, 2, because there are 3 here, 1, 2, 3, and the 4th is the bias. So this is the bias. Okay, so that's how the thing is structured. So this is how you create the weight matrix for the network. Okay, this is a random weight matrix. These are not going to be the weights, because when we train it, you know, the weights are going to be adjusted and they are going to be changed with every epoch. The weights are going to get updated. So are you now understood the initialization of the network before we move to create the entire forward propagation? Have you understood how to initialize a network? Because this is a very crucial step where you're taking random weights and doing it. So I'm going to do a small poll, because I'm being a very bit of sensitive, because you know, for me this is super important that you get each step, because if you don't, then I'm producing a bunch of people unfit for the future. That's why we are so sensitive. You'll have to permit our sensitivity to this. Yeah, we had started a small poll to check whether you have understood the initialization of the network, and then we will move on to the forward propagation and move forward. Okay. So far I have about 80 votes. A good number seems to have so far understood. Yeah, so we have a poll. I think we'll finish the poll and move on, because I got about 170 votes, 167 votes. Okay, so it looks like most of you who voted have understood. Now the pity is the rest of you have not voted. I don't know whether you're listening or you're just logged on. Okay. No, why I don't get why 4 is added. 4 is the second layer. The second layer also, no? Yeah, I'm asking total number of weights.
It's like inputs plus 1.
Number of inputs plus 1.
Yeah.
See, the bias also is added, no? For every neuron, there is a bias. ZWX, Z is equal to WX plus B. For each neuron, the B will be different. Just like the weights will be different, the bias will also be different. So that's why you see in the equation also it's n number of inputs plus 1, then number of hidden plus 1. So that's why that extra, and because there are 2 layers, that many things get added. No, 24 is of that layer and 4 is extra. 4 is of the next layer.
I thought that 7 into 3 is 21 and 3 into 1 is that.
Acha, you thought 7 into 3 is 21. Bias also you have to add. Each neuron in the output layer, in every layer, has a bias also, which doesn't change with the input, which doesn't get multiplied by the input, but each neuron has a bias. Okay.
This question is why that 4 is added further. After that, 7 into 1 plus 3 is 24. That I understood.
7 plus 1 and 4. That's what I'm saying. No, it's a 4 is, I don't know whether you are saying 4 is of the next layer. See, weights are there in the output layer also. No, our network is what? 732, right? 731. So the weights are there in the output layer also. No. That 4 is from the output layer. Why is bias? Because that's the equation, Baba. Bias is some kind of a value which is added so that even if the weights are 0, the input will be there. No, no. No, obviously, each neuron will need its bias. Okay, I think there is a little clarity required here. Okay, it's like this. See, suppose I have an input. Okay, I'm just giving a little clarity here because it's super important that you get it. See, we have how many inputs? We have 7 inputs, right? And how many neurons are here? Let's say in the current example which we are doing, we assume 3 neurons. So each one of them is connected to each, right? So this is what it is. So what is the equation for every neuron here? Z is equal to W1 X plus B. Actually, it is sigma of that, but we'll come to that later. So because this is X of all, W1 is the weight matrix. This is I'm referring to the whole matrix as W1 as this plus B. B is bias, which is there for every term, right? So if you write the expanded version of this, let's call this Z1, Z2, Z3. Okay, let's get a little more clarity, which will anyway needed for the next, when I explain the forward propagation further. Look at this, Z1, Z2, Z3, right? This is what is Z. This is like the equation. So what is Z1? Z1 is equal to, let's call this X1 through X7. Okay, and let's call these weights W11 if it goes to Z1. So it is W11 X1, okay, plus W21 X2, and so on up to W71 X7, okay, plus let's call this B1. So this is the macro equation in a matrix form, but at a scalar form, this is, you can say it's a vector form of the equation. Scalar form of this equation is Z is equal to W11 X1, W12, no, sorry, W21 X2, W31 X3, and so on up to W71 X7 plus B1. Okay, so that is what is the equation for Z1. What is the equation for Z2? It will be W12 X1 plus W22 X2 plus W32 X3, so on, plus B2, this bias. So each Z1 will be like this, Z2 will be like this. So each of these Z1, each of this neuron, what are the weights? How many weights will it have? These 7 plus this one, these many weights. Actually, in the real sense of it, only these 7 are called weights because they are multiplying with X1. Bias doesn't multiply, and irrespective of what X1 it comes, bias remains the same, right? But this is also a training parameter. In the sense, this is also not known. So this is also randomly generated. And this is how this equation looks like, right? And Z3. So this here also there are 7 plus 1. So totally there are 8 weights. I hope now things become clear. Correct, the Mr. Racharla. That is what it is, because each neuron will have its own bias. Like I have shown you here. Here, look at this is the bias associated with Z1. This is the bias associated with Z2. Similarly, here also there will be that same thing. There will be, if you have one output, each one will be connected, plus there will be the bias term, right? So if you take this, you know, that since there is only one neuron, this we can call, well, this is, we need to add one more layer thing here. So let's say this is layer 1. So let me add one more suffix here, 1. These are all 1. Now this is layer 2. Okay, so here how it will be called? W 1 1 2 into Z1, or whatever is the output here. Actually, it doesn't go directly there. There is again a activation function which works, and then it goes here. Okay, but it's similar. So that's how this whole thing happens. Okay, now I hope things are clear to everyone, especially Vikas. Did you get that? Oh. No. Okay. Then look at it carefully, because you will have to get the bias understood. Okay. Now I can't go on further because I think we have spent quite a bit. Just think it is bias plus 1. Sorry, number of weights plus 1. Okay. That is the bias. And why is the bias needed? Because imagine random generated weights. Weights are very small or zero, random. There has to be some input which will go through the layers. So that is why we need a bias to be added. It's like in any equation, we have bias because, we never have perfect symmetry. Okay. So, okay. Now let's, what I'm going to do is, I'm going to, yeah, good. So let's move on to the next part of the network, which is next part of the code, which is basically the forward propagation. Okay. Now I'm going to show you the forward propagation. There are 3 steps in the forward propagation. Now this paper uses some terminology which I don't entirely agree, but I'll take you through the code, and then I will also familiarize you with the terminology. Okay. Okay. So let me elaborate. There are 2 parts or 3 parts in the forward propagation. So let me elaborate on each of those parts at length and show you what is happening, and then you will understand each segment clearly. Now, please, even though this is taking a bit of time, I am prepared to spend a lot of time here because it's fundamental that most of you or all of you get these things going. Because if you don't get this going, and I'm sorry, I have to repeat this again and again, we are going to lose you as far as AI is concerned. Because I have trained now maybe several thousand people in AI over the last 8 to 10 years, and I have discovered, or I have noticed, that one of the reasons they don't understand or they don't get AI well is primarily because they don't understand this flow properly, and probably because the instructor or whoever has taken the responsibility has not spent adequate time. Most of our faculty, I have noticed, just gloss over this and don't spend adequate time on giving you the insight here, and then we ruin you for as a AI developer. Then you start looking at AI only as a chatbot and start developing front ends to the AI, and then those jobs don't get you anywhere. Okay, so now let's look at the activation, and let's look at it again very carefully. What do you mean by activation? But before that, what a bit of their terminology. What do they call activation and what do they call transfer? Okay, so basically, I don't know why the flicker. There is a lot of flicker, no?
That's project.
Projector. Okay, so yeah, suddenly it has. Okay, so this is what is the way their terminology is. So the computation of Z1, they don't use Z1 in the book. They call this, the computation of Z1 is called computation of Z1 is called activation. Okay, and I think I told you last session, after the Z1 is computed, before the output of that hidden layer comes out, there is the Z1 gets multiplied by a sigmoid, which is, remember, the Z1 captures only the linearity, and we have nothing to capture the non-linearity. Therefore, we introduce the sigmoid, which is the non-linear function. Remember the equation 1 plus 1 by 1 plus to the power e power minus x. So sigmoid, this is called the sigmoid. Sigmoid of Z1 is taken, sigmoid of Z2 is taken, sigmoid of Z2. That is called they call it transfer. Okay. Now this is slightly different from the standard nomenclature. They call computation of Z1 as activation, and then the application of the transfer of the sigmoid or the non-linearity as transfer. Well, today we'll stick with that terminology, but later you'll learn that we call this the linear function, and this we call the activation function. So anyway, it doesn't matter for today. So this paper chooses to call this as activation and this as transfer. Okay, so the linearity is called the activation and the non-linearity is called the transfer. Just remember that. Linearity is activation and non-linearity is called the transfer. Okay, both have to be applied on every input. Okay, so now he is showing how to compute the activation. Okay, now the activation, the way it is carried out, which is the linearity. How do you do the linearity? So this is how the linearity is computed for Z1. He is now using this and going to compute Z1. So how is Z1 computed? How is Z2 computed? How is Z3 computed? Okay. So now if you think inputs are 7, okay, this is inputs. Weights are the this layer, the weights of this layer. Okay. All this. So each Z1 is associated with 8 weights, 7 plus 1. Now, how is the activation computed? What is the activation? What is the equation for Z1? Z1 is equal to W1x plus bias. So the weights are multiplying only to the x input. So now look at this. Activation is equal to weights minus 1. Means that he is taking the first activation, that is the last of the weights, which is the bias. Okay, and that he is starting with activation. So this is, he's taking this term and this is the bias term. Okay, remember the last weight is always the bias. Okay, that is how the number of inputs plus 1, if you remember. This is that plus 1 of the weights matrix, of the weights list. How we will get to that list is different, but given the weights list, the last weight is taken as a bias, added to the activation as it is, and then the rest of the weights are multiplied with the corresponding input W1 X1. So for now, look at this. For I in range, length of weights minus 1, then activation is equal to activation. There is a plus equal to, because we have to keep on adding. Remember? Now let's elaborate. Now Z1 is equal to, not like this, W11 X1 plus W21 X2 plus W31 X3 and so on. So each of the weights, now if you keep this one aside, this one corresponds to the Z1. So if you take this, each weight has to be multiplied with its corresponding input and so on, and the bias has to be added. So he's building this equation. So this is how it is done. For I in range, length of weights minus 1, weights minus 1, because he's now already taken the bias into consideration here. and each of those weights is now being multiplied by the corresponding input. Each weight is correspondingly multiplied by its input, and that goes to get the Z1. So each neuron here, you see each neuron here has 8 weights associated with it. Each of these weights has to be multiplied with x1 to x7 plus the bias, which is the 8th weight. So he's keeping that outside and multiplying all of these and getting this value built. Now this is going to get only one Z1, and if he does this for all the neurons in this layer, he is going to get basically the whole of this layer, right? He's going to get Z1, Z2, and Z3. So okay, so that is how this is coming. Okay, so there is Z1, there is Z2, and there is Z3, and similarly we go with the next layer. So I hope the activation is understood. That is the linear computation, how to do for the calculation of Z1. Similarly, we'll have Z1, Z2, Z3. We'll run this in a loop for all the neurons of this layer, of the hidden layer, and get this computed. So we will get the Z1s, Z2s, and Z3s computed for each of the neurons, and then we'll pass them through the non-linearity using a transfer function. We'll do that. That is the sigmoid. We'll do that in a moment, but first you need to understand how the forward propagation is flowing. Okay, so this is the forward propagation flow for just the activation, just this computation. Okay, so this is what you will get as a value. Okay, this is Z1. Now since we are clear about pretending that we are clear about this, I'll just go and show you how to apply the non-linearity on this, and then we'll take it forward. Okay, so now we are seeing the non-linearity getting applied. This is the non-linearity. Now you come to the non-linearity. So for each of the activation which you have computed, we have to apply the non-linearity. What is the equation for non-linearity? Sigmoid of Z1, sigmoid of Z2, sigmoid of Z3. So whatever value, this is a scalar. All these are being converted into a scalar. So how is this computed? This is the simple equation. Sigmoid of x, or sigmoid of anything, is equal to 1 by 1 plus e power minus x. So this is how it is implemented in Python. Simple Python, 1 by, because we want floating point calculations, 1.0 divided by 1.0 plus exponent of the activation. Because remember, the way every layer works is first the linearity is applied. This is the linearity, and then to the linearity the sigmoid is applied to produce one output, and one output. So that layer will produce 3 outputs, which will go to as input to the output layer. I mean, this is the hidden layer output. There will be 3. So this will be the output. So there will be 3 outputs which are produced, okay, from each layer. Now this is the logic behind forward propagation, and the same logic is used layer after layer. Okay. Now if you are clear about how to apply linearity and non-linearity, we will look at the forward propagation. Okay. How can you explain line 5 again? Okay, let me try whether we can go to the previous thing and explain line 5. Ooper. Okay, line 5 is no, it is, if you look Z1, see what is Z1? Z1 is, we have taken bias out of the equation, but what is the equation for Z1? W11 x1. Now you keep this one aside. This is for the first neuron. This is the weights associated with the first neuron. So W1 to x2, isn't it? And plus bias. Now the bias, we have it in the weights list as a separate last item. We got that. Okay. And then we are multiplying. We have kept that added already into the activation. This is computing that Z1. All this is to compute the Z1. Now, how do you compute the rest? You have to take the weights and multiply it with x1. Take the first weight, multiply it with x1. Take the second weight, multiply it with x2. Forget this for a moment. This is W12. No, sorry, W21. I'm sorry. So because it's all going to Z1. So you're taking all the weights associated with that first neuron, taking all the inputs. See what you have to do to get this. Your input consists of 7 neurons, right? 7 inputs. So I have to multiply each one of them with its corresponding weight and get this value, isn't it? I mean, sorry, this value. I have to get multiply all of this. How will I do it? I have 7 inputs. I have their corresponding weights, W weights I, which I'll get. I'll show you how to get that. Imagine these are the weights associated with this neuron. That's how I have stored them. Remember in the dictionary? And if I multiply all of this with their corresponding weights, will I not get this equation? Z1 is equal to W11 X1, W21 X2, and so on. Bias, you see that is how it is added. First they added the bias and then added the multiplication of that. Look at this plus equal. And that is how we got this. Now once we get this, we apply the transfer function, which is the non-linearity. So this is the linearity. And then to this we apply the non-linearity. Once we apply the non-linearity, we get the output for Z1. That is, it will be sigmoid of Z1. That will be output of that layer, O1. Similarly, O2. Similarly, O3, which will become the input for the next layer. Okay. So, yeah, there is another question. What factors should we consider while choosing the weights? Well, initially the weights are taken random. Okay, later there is some logic in the way we choose weights and all of that. They are a bit, I mean, see, during training, we normally or almost always start first with random weights and then apply correction to it depending on the error and keep on applying correction. And that is how we arrive at weights. So it's generally starting with random. Okay. Uh, Obviously, later when the model is developed, you will not choose random weights. You'll pick them up from what they call a checkpoint. Okay. Line 3 also. Line 3 is nothing but the bias. I'm taking the bias term, which is the last term in the weights. See, how many weights are associated with this layer? 8, correct? The last weight is the bias. And the first 7 are the ones associated with the weight I am going to give for each input. Right? So that is how I got 8. Okay? I hope it makes sense. So now I have shown you how to compute for every neuron in the output of each layer, how to compute the linearity and the non-linearity. Now it's time to put it together and then I'll pause whether you have understood the forward propagation or not. Okay, so let's try it out. Let's not try it out. Let's see the computation. We'll first explain the forward propagation code. Okay, now this is the big code. Okay, so this is the weight. This is the forward propagate. Now I will pause here for about 4 or 5 minutes. This is normally what I do in my classes. I'll pause for 4 or 5 minutes. I'm going to give you time to look at this code for about 5 minutes, and then we are going to because I want you to make some impression in your mind, right or wrong doesn't matter, some impression in your mind, and then we will understand this code together in correlation, because this is a important part of the forward propagation which does it layer by layer. Okay, your network is a list of layers, and I will give a little bit of insight and also on the data structure and all, but I would like you to look at it for the next 5 minutes. I'm going to shut up for the next 5 minutes and I'm going to leave it to you to make some conclusions. Right or wrong doesn't matter, but think about it, and then we will discuss it together. Yeah, I hope you had some time to think over it. Okay, I'm going to ask you before I start explaining. I'm going to pause a bit and ask you, how many of you understood this code? Honestly, tell me. It doesn't matter. Okay, we'll just do a small poll. How much? How many of you understood? Just say understood. Yeah. Okay. Yeah. So far, some people have. No, good, good. If more people have understood, it's good. Then, but I'll nevertheless explain in detail because it's very imperative that you understand this code. Okay. Equal number of people so far understood, not understood. Let's wait for a couple of minutes and then I'll walk through the code. The no's are also good because then I am here with a purpose. If everything is yes, then what is the purpose, isn't it? Okay, I am liking the no's by the way here. Okay, another 30 seconds and we will uh, resume. I think we are good enough to make a beginning. About 60%, no, 70% of the people didn't understand, and about 30%, I'm going roughly, 30% of the people have understood, which is kind of good. Okay, so let's now walk through the forward propagation, where rho represents initially the input, and network is of course network. Network consists of layers. So I'll briefly talk about the network data structure. How does it look and what does it consist of? And that is the fundamental to understanding this chunk of code, this piece of code. Now, if you understand this piece of code, we have made tremendous progress because then we have understood the whole forward propagation business, and it's an important milestone to reach. Okay, so let me now elaborate a little bit. I'm going to take a bit of time to help you understand this because it's super important. Okay, now what is this all about? Network is network. Let's visualize the data structure of a network. The data structure of a network is a list of lists. So this is one list, comma, this is another list, this is another list, representing how many layers. In a two-layer network like we have, we only need two lists. Okay, so okay, let's say in our case we don't need this because we are going to have two lists, because there are going to be only two layers. One is the hidden layer and the other is the output layer. But in a multi-layer network, which this code will work even then, the beauty of this code, and that's the reason why we have taken this code can work with any number of layers. Of course, it will be very, very slow, and we'll know why it is slow and we'll study why it is slow. And then I'll go forward. But at this stage, what we have is we have our network is like this. So this is our network. This whole thing is our network. Each is a layer. Each is a layer. So this is the first layer. This is the second layer. And each layer, now let's look at each layer. What does each layer have? Each layer has a dictionary. So each layer has a dictionary. The dictionary consists of this. So each layer is a dictionary of weights. Okay. So meaning the dictionary has only one key field, weights, and it has again a list of weights associated with it. So each layer is, so a network, the whole network is a list of lists. Okay, each layer is a list of lists. Each list consists of weights. It consists of, sorry, each is I think this is a dictionary. Each layer is a dictionary. And each, so sorry, so it's a list of dictionaries. So each layer, yeah, each layer, no, sorry, because there are more neurons. I'm sorry. Each layer is uh, uh, each layer is a list. I'm sorry, it's a list of uh, uh, dictionaries. It's a list of dictionaries. Each layer is a list of dictionaries. Now, dictionary depends on how many neurons are there in this layer. So if the hidden layer has 3 neurons, there are 3 dictionaries here, which is a list of 3 dictionaries. Each dictionary, because see, if there is Z1, Z2, Z3, and there are 8 of this here, then what we have here is, depending on the number of inputs, plus 1 are the weights here. So this list is about 8 weights. If there are 7 inputs, this is 8 weights. Okay. So each of these neurons have 8 weights associated. Okay. Each of these neurons of this list. Okay. I'll repeat it once again so that you understand, because this is a very nice and cute data structure which they are using. Okay, again, so the whole network is a list of lists. This is the list. This is a list of what each layer is a list. So this is a hidden layer, this is the output layer. In this case, only 2 layers, but there can be several hidden layers and 1 output layer. And now each of these lists consists of the number of neurons in that layer. So if the hidden layer has how many neurons? 3 neurons. So it is a list consisting of 3 elements. Each element is a dictionary. The dictionary consists of only 1 entry, which is coupled with a list. The weights points to a weights is associated with a list of 8 weights. 8 weights because each of these neuron here has to cater to 7 inputs plus the bias, so 8 weights. So this is how the data structure looks. This is fundamentally you have to understand. So if you have understood this, that each neuron here is represented as this dictionary. This dictionary has 8 weights, each neuron feeding into each neuron. There are 8 weights which are used to multiply the input, the corresponding input, and feed it into this. Take the input, feed it into this, take the input, multiplied by the corresponding weights, and feed into this, all of that. So that is how these weights are developed. And these weights are listed. So to put it simply, I'll write this in English. Layer, sorry. This. I'm just going to write this in English. Okay. Network, the whole network is a list of layers. Now, each layer is a list of dictionaries. Why a list of dictionaries? Corresponding to the neurons in that layer. Each dictionary has weights, has how many weights? Has number of inputs plus 1 weights as the list associated with weights. So this is how it looks. Okay. So if you are having this data structure in front of you, this code becomes that much more easier to follow. Okay. Now, if you have to forward propagate through the network, this is how you have to start. You are given the network and you are given the initial row. Row is what? The input, which is the 7 values. In our current sample in this code, there are 7 values, which is the row. So the row will consist of 7 values. It's a list of 7 values. Okay. So that is your row. That is the input to the network, which has to go through all these layers and produce an output, depending on the output layer. Okay. Now we start with inputs equal to row. So that is set outside. So this is a list. Okay. Inputs is a list of all the x1 to x7. That is a list. Now we go layer by layer. Okay. Now we start with layer for layer in network. So first time we are at the first layer. Okay. For layer in network, because network is a series of, is a list of lists. So when you say for layer in network first time, layer points to this list. This is layer first time. Okay, this is layer. Now that layer consists of what? That layer consists of again a list. Okay, we'll follow. That layer is consisting of a list. Okay, so for layer in network, new inputs is setting empty right now. We'll see how it uses it. This is to move from one layer to the next layer. What is output of the first layer will become the input of the next layer. Anyway, we'll come there. Let's not worry about this right now. Now, for each neuron in the layer, so now this, we are now on this layer. For each neuron, how many neurons are there in this layer? There are 3 neurons in this layer, right? This is the first neuron associated. This is the second neuron. This is the third neuron. So these are the neurons in the layer. Remember, the input layer has 3 neurons. The hidden layer, not input layer, I'm sorry. The hidden layer has 3 neurons. So these are the 3 lists associated. For each neuron in the layer, now each neuron is what? Each neuron is the list. This is the list. This is the first neuron. So now first time the neuron will point to the first list of weights which are there in this layer, right? This weights, right? Now what do? Now remember, we written the activation. We compute the activation. Activation is equal to for each neuron. Now, sorry, for each neuron in the layer, we compute the activation. Activation is equal to activate neuron weights. Now, when we say neuron weights, this neuron is this. Neuron weights will be this list. Okay, so this is a list of weights, okay, associated with this neuron, which we are currently processing. So if you are processing the first neuron, that is Z1, this is the list corresponding to the weights associated with Z1. So we are passing to the activate function these neurons, the weights are associated with this neuron and the inputs. How many inputs? Inputs is a list of 7 values. So it will add the 8th weight plus the multiplication of the 7 weights with this inputs, and that is what activation will yield. So activation will yield the Z1 for the first time, because first time we'll take the first neuron in the first layer and do it. Then at that point, we'll get neuron output we are creating. This is creating the neuron output. This is the activation for that neuron based on its weights. Now we are creating another field in neuron, which we can create whenever we want. So because neuron is a list, and in that we are creating, we already had weights. Sorry, each neuron is a dictionary. Each neuron is a dictionary. And in that we already have an entry for weights. Now we are creating an entry for output of that neuron, which is equal to transfer of the activation. Whatever value we got as activation, we will get there. So at this stage, we'll have, for every neuron, we'll have its weights associated and another field associated called its output. Okay. For every neuron, there will be now 2 fields in the dictionary. We are updating the dictionary because each neuron is a dictionary, right? Dictionary in which so far there was only 1 entry, which was weights. Now we have added another entry called output. So there is another entry called output, and associated with the output, what have we associated with the output? The computation of activation followed with the transfer function, that sigmoid. This is a sigmoid activation. So that value is coming into this output. So now each neuron will contain this and output, which is in this case Z1. That will be the output. Now what will happen? Okay, now we are creating a new inputs, which is, remember, empty, which is a list. To that we are appending this output, this output value, that is this Z1. We are which is passed through the transfer and all that. We are adding it to our new inputs to append. Now these new inputs will become the current output, which will become in the next time for the next layer the input. So new inputs dot append. So what will new inputs have now? New inputs will have a list which is consisting of first this Z1. Okay, because it is the neuron output is getting added to the new inputs. this value, whatever it is, that is Z1, is getting added to the new inputs as value. Okay, this is the first time. Okay, now this will iterate again. Now we'll go to the next neuron. That is, we are now here. This is the next neuron. The next neuron is also a dictionary. Now, what will we do? Now, the next neuron, we will take the weights associated with the next neuron. See this, neuron weights. We'll take the weights associated with the next neuron, that is a second neuron in the hidden layer, and then multiply it with the inputs again. Because remember, this neuron also has to take all the 8 inputs, 7 inputs plus the bias, and it will produce some output, which is the activation, and then we will produce that neuron's output. So there will be another output getting created here, which is a scalar value, which is equal to a transfer of the activation. So some value will be there. Now that value, we are calling it Z2. Okay, that value we'll call it Z2. That Z2 gets added as the layers new inputs next value. Now this is, we have worked with the second neuron in the hidden layer. Now we go to the third neuron in the hidden layer. We again take the weights associated. Remember, there are three dictionaries. So now we go to the third dictionary, third neuron weights which are associated, and multiply again that with the input. All of that has to get, because there are 3 neurons, all of them get multiplied by all the inputs here, and then again pass it through the non-linearity, which is the transfer. Take it and then add it. So this becomes the Z3. So that is what is the new inputs. Now, at the end of this, we have finished with this layer. So we are done with this layer. Now what we do is, now we say inputs is equal to new input. So now the inputs gets, which was row earlier, which was the actual input, now gets substituted by new inputs, which is all this Z1, Z2, Z3. Now we go, so the inner layer is over, the inner for loop is over. Now we go back here, and now what is inputs? Inputs is now the output which has come from this, which is Z1, Z2, Z3. Now that becomes, now we are on this list. This is the next layer, right? This is the next layer of the network. So we go to this next layer. So now we are on this layer. Now what happens in this layer? Same thing happens. Only thing is, instead of multiplying with x1, x2, x3, now we multiply with Z1, Z2, Z3 and the weights here. So here also the structure is the same. Depending upon the neurons here, the weights are there. For example, if there is only one neuron here, there will be only one dictionary here, that is one neuron here. So one dictionary here. So we will produce that thing and produce its output. So we will do the forward propagation and produce the outputs. And that final output is going to be, if we are returning input. But you know, when we finish with this, inputs is nothing but the, if you see the setting here, will be the output of the forward propagation, which may be a single value, or depending on the number of neurons, which may be a set of values, whatever it may be. Okay, so that is what is forward propagation. To appreciate and understand forward propagation, it is fundamental to understand how the data structures are created, how the layers are, and how the layers have been built as a list. List of what? List of dictionaries, each dictionary representing weights to which we are adding the output of that neuron, and that is what we are taking forward and forward and forward. Okay, so that's what is happening in forward propagation. Okay, so if this piece of code is clear, then we can make some progress. Now I'm going to pause again and take a small poll. No, open the chat. If you have any questions, I would take them in the chat and see if we can answer some of them and try to give you an insight. So does that mean line 11? Yeah, finally it will return y hat. Excellent. Emaduddin, the correct understanding. So the final return of line 11 after we have done everything will be the y hat. Yes, it will be the y hat, the final prediction. It will be a single y hat, or depending upon the number of neurons, it will be the vector of y hats. Okay, or a list of outputs. Okay, so that is correct. So before that, Lokesh, Nalgonda Lokesh asked a question. Uh, Forward propagation function is taking the network as an iterating over each neuron, no, each layer in the network first. Lokesh, you're right in saying it is taking the network as an input, iterating over each layer first, then iterating over each neuron in that layer, and then we are computing the output and making that the input to the next layer. Okay, so that is a little change. So visualize this again, and I'll say it again. Network is a list of layers. Each layer is a list of neurons. Each neuron is a dictionary of weights, and each weight is associated with a list, which is the weights list associated with that layer. With that neuron in that layer. Okay, so this is the overall code of doing forward propagation with some kind of input and some kind of output. See, the none is because there is no bias. These are some pre-defined weights which are there, maybe coming from the earlier calculation. These weights, yeah, these are some weights based on the network of 212, not the network that we have, but a network 212 means two inputs, one neuron in the hidden layer and two neurons in the output layer. So that's how that is. Okay. Yeah, the output belongs to list or variable. The output is also a vector actually, because inputs is a vector, right? So it's a vector means a list. Okay, so the output is a list, so it's a vector. Yeah. Okay, now let's pause a bit and see whether you have got a sense of forward propagation or not. That is, have you understood how to create a network, how to activate, how to transfer, and how to do the forward propagation of a network? Because this is itself an important milestone, you see, in understanding how to do the forward propagation. Okay, so okay, so let's pause here and do a small poll of the forward propagation. For the first layer, the weights are random. For each layer right now, the weights are random, please. All weights for all layers are currently random. When we correct, then we will decide. Then we'll make corrections to the weights. We'll come to that. But as of now, all the weights for all the layers are random. What exactly is happening in the transfer neuron activation? Transfer is basically applying the non-linearity, and activation is applying the linearity. So when you say activation, it means I'm computing Z1 only as Z1 is equal to W1, 1, X1, W1, 2, 1, X2, like that. That is called the activation in this nomenclature. And transfer means applying the non-linearity. See, the whole idea is, why do I apply a linearity? Why do I apply a non-linearity? Because we believe that the whole world, anything in the world, any input to output relationship is to be visualized as a gigantic function. See, what is the basic premise of AI? What is it that the Elon Musk of the world or the Jeffrey Hintons of the world are telling us when they say we are creating AI? It is basically an impression that given an input, I can describe an output by creating a network which is a cascade of functions. Some of the functions are linear, some of the functions are non-linear. I don't know what the functions are. I don't know how much of linear non-linearity is there. So all the linearity I absorb using W1s, all the non-linearity I absorb using sigmoids, which are what we call the transfer functions here. So that's the basic premise of the world. And anything in the world can be visualized from any input. That's the abiding premise. So if you want a larger picture, that is what is happening in the larger picture. Okay. So, okay, now let's see the poll again. See how many have figured out. Has it improved since we talked? Okay, it has improved quite a bit since we talked. So of the 99 or 100 votes, I see 90% seem to have got it, which means we have been able to communicate a lot better than what we were at initially. And obviously, the disturbing point is there are so many people leaving.
Out of 300, and we have got
Poll of
30%
only
of
50%, not even 50%. Okay. Yeah, we have the activation, we have the transfer function, we have the forward propagation. So we have the whole story of doing it. Forward propagation code will run on, yeah, it has to run on a GPU, but we'll come there. I'll show you how to parallelize this code and run it on a GPU. But first, let's get it without the parallel. And then each of these multiplication WX, as we talked about earlier, can be done cell-wise. That means Z1, okay, since somebody is going a little ahead and thinking, if you now think in GPU terms, if you look at this code, okay, now let's look at this code again. If you look at this code, you see loops here, right? If you see, this is the linear code, this is the naive code, okay? Now, if you see here, each neuron, until I compute Z1, yeah, sorry, not till here, maybe till here, sorry, the inner loop. This is for computing Z1. Then the next neuron, Z2, Z3. This is all getting done one at a time, meaning sequentially. This is the naive code. Naive means bacha coding, right? This is like people write when they don't know GPU. This is naive code, okay? Because first Z1 is getting computed, then Z2, then Z3. Imagine that this part of the code, this code, instead of being done in a loop, the Z1 computation, the Z2 computation, and Z3 computation all happen in parallel. Okay. Now I can't do layer by layer parallel, right? Unless the first layer is done, you can't go to the second layer. So that has to be done sequentially. But within a layer, the computation of all the neurons now is happening also sequentially, if you observe. So that is naive code. But if I do this parallelly, forward propagation, if I do it parallelly, I can do it on a GPU. And I'll show you how to do that. In fact, now that you have raised this issue, maybe our next session, we will show you how to do exactly this code in a GPU style. Okay, so that how to execute this code on a GPU, not stupidly like we are doing here, right? This is naive. Naive is a euphemism for stupid, idiotic, and dumb. I am running short of adjectives. So basically, smart way of doing it is this one, and this one should be done in parallel for each layer. And of course, the layers have to be done sequentially. Unless you compute the first layer, you can't do the second layer. But within a layer, you can have parallelism, right? And that itself will be huge, right? Because the computation of Z1 is not dependent on Z2 or either way. There is independent. These are all independent, right? So each row by each row. So that can be done on a GPU. Okay. So yeah. So that's why GPU is fast. Yes, that's why we run code on a GPU, because right now the forward propagation is being done in a very, very naive manner. Okay. So why should we do this? I mean, apply activation and transfer. Where can I imagine its place as a beginner? Well, I think I told you, Sudipta, the reason I'm doing it is basically because I'm trying to abstract the real world. And I believe that the real world is a combination of linear and non-linear. Okay, so that's the basic premise. Okay, and okay. So, okay, now we have got a poll, and I think we have made a sense out of this. So now let's initialize our network and give some input. Okay, here we have a testing of the forward propagation. It's a smaller network. This network consists of two inputs. Obviously, for bias, there is no input. So, but because of the linearity of the matrices, because each of them have three, so he's given 1, 0, none in the row input. So actually, the input has only two. So the number of weights in the first layer is 3, and the network is 2, 1, 2. So in the second layer, so if you see, okay, let's see this data structure again. So, I mean, this is a sample network they are using. Let me rub this part and show you what is happening. Okay, let's look at this test. Can you come down? We focus on the network. Okay, now this is his network. Remember, he created for this. Wait. The initialized network was 2, 1, 2, which means that the network has two inputs, one neuron in the hidden layer and two neurons in the output layer. So this is how it is. Just drawing it like this. So that is the so with this neuron, how many weights are associated? 3. So that is the 3 neurons. This is so this is layer 1. That layer 1, because there is only one neuron, there is only one dictionary. Okay, there is only one dictionary. Now here there are two neurons, so there are two dictionaries, one associated with and bias. This is bias, okay, and one associated here, and and it's bias. So that is so a layer 2. This is layer 2. This layer 2 has how many dictionaries? Two dictionaries, because there are two neurons associated, and each dictionary has two weights, one with this neuron and one with the bias. So this is how this dictionary looks. This weights and this weights. This is another dictionary. This is one dictionary. This is another dictionary. So there are two dictionaries. And so it's a list of two dictionaries. This is a list of two dictionaries. This is a list of one dictionary, like you hear, with three weights, two for this and bias. Okay, so this is how it is. And then he is calling this 1, 0, none is none, so that all inputs are 3, 3, 3 standardized, because that's the maximum. So output is equal to forward propagate network row. So that's how this will work, and print output. So you'll get some junk output. Output will be a vector again here, because there are two neurons here. Of it will be a list of two values. Okay. So we'll run this and check what the output is. Okay. And the input is 1, 0. Okay, let's run this piece of code on our tool, and we will see what is the output. Just observe the final output. Okay, as you can see, the output is a list of two values, because our output neuron spews out two values. So that is why the two values. Okay. So I think this is the forward propagation. Now somebody had asked a question, Shashank. The range function by default does not include the last value. Yes. So why are we subtracting 1 under the activation? Because we already taken care of the last value. No, the last value of the activation is the weight for the bias, is the bias. So that's why we are taking it. So the weights are from see, if the thing has 8 values, 7 are for weights, that is labeled 0 to 6, and the 7th one, the last one, is the bias. So that is how it is taken. So to get your maths, the number of values. So this is for the person who asked this question. The total number of values are 8. So how, and let's say inputs are 7, so values will be 8. So how is this distributed? 8. 8 is, the last one is a bias. So the value with last is bias, and the range of the values which are remaining is 0 to 6. So that is why the length of weight minus 1. So if you give 7, then it will go from 0 to 6. Correct? I think that will make sense. Okay. So that's why we have that. So this is a forward propagation. As you can see, the output is junk. Okay. And we are getting the same output because we have used the same seed. Okay. That's why we are seeing the same output. Okay. So this is now forward propagation. Okay. Now we will have to go through the whole error computation and backward propagation of error, which I will do in the next session. Also, I have not done any exercise Jupyter notebook now. We'll do it in the next session once we know how to change and all of that. Now, I have a very interesting question for you. In the next session, do you want to see only the forward propagation in GPU form and backward propagation, or do you want to see forward propagation and we'll do the whole GPU later after we have done the backward propagation? I think I will not give it as a poll. I think we'll do the backward propagation regularly, and then we'll convert this whole code into its GPU variant so that you understand how a naive code becomes GPU code. This is the plain vanilla code without use of a GPU. I told you how a GPU will improve the performance. That is, the Z1, Z2, Z3 all will be computed concurrently or simultaneously, thus reducing the time rather than sequentially. That's where the whole story of GPU, and that's why if that was not there and this is not how it was working, then NVIDIA would not be the #1 company today. So the reason it is the #1 company is right there in front of you. That the forward propagation will be so slow, especially when the total number of neurons runs into 1,000 and the number of layers run into 1,000. So that you have in right in front of you, as we have in every session, the clarity why this guy is rich, right? Yeah. So if you had figured it out to do parallel today, you would be a rich person and we would be discussing you. But neither you nor I had the ability to figure that out, that this would be needed. So here we are. Okay. Yeah. So now I think we have reached kind of a milestone. So we'll stop here.